Okay, so we're recording a new topic for a new chapter to start off with today. So that's exciting. But you'll notice we're skipping chapter 4, right? We just finished chapter 3. We're jumping right up to chapter 5. That is because of a combination of reasons. First factor in the reasoning is that chapters 6 and 7 are challenging and chock full of ideas and takes time to digest, and we need to get to it as soon as possible so that we can have as much time after chapters 6 and 7 as possible for y'all to digest those ideas. Second factor, chapter 4 is not prerequisite to chapters 5, 6, or 7. So delaying chapter 4 to the end is just kind of it's just strategically beneficial is the point. So anyway, we will come back to chapter 4. We will come back to chapter 4 after we finish the rest of the chapters, but we're just going to skip it for the moment. Okay, so all that said, how do we do integrals? I'm going to start with a convenient example. Kind of like I did I wrote this, look at that, I wrote partial derivatives in chapter 3. I meant chapter 2. Sorry about that. I'll get that fixed. That was a oops. Anyway, in chapter 2, I started with partial derivatives, but I gave you all this warning of don't hang your hat, please, on the idea that partial derivatives are the fundamental way to think about derivatives. They're really not. They're elemental in a way. They're computationally convenient. There's nice things about them. But the fundamental way of thinking about derivatives is with the derivative matrix, right? Fundamentally, derivatives are relationships between input changes and output changes. That's what the derivative matrix does. So, just like that, I'm going to start off with a convenient example. Don't hang your hat on this. There is a much better way to think about multivariable integrals. So, that noted, let's do it. Old news. Y'all recall this calculation from single variable calculus, I imagine. If you have a rotated surface, like so, right, then that bounds a certain volume. And you might want to compute how much volume that is. How are you going to compute that volume? I'm going quickly because this is all old news, and hopefully, presumably, you all remember this. The idea is you say, well, I'm going to look at little slices of volume that look kind of like this. And these slices of volume I can think of in terms of a cross-sectional area that I'm going to try to draw here. So there's a cross-sectional area which I can write down a formula for because it's literally a disk, right? Easy high school geometry class formula for that cross-sectional area. And then I multiply times this thickness, which is dx, because it literally comes from chopping up the x-axis into little pieces. And, well, area times thickness gives you little pieces of volume, right? And then that little piece of volume, that dv, which is dv, which is all of this, is you add those up. You add them up, of course, with an integral where you let x go all the way from a to b. You add it up, and boom, right? Everybody cool? Okay, old memories. Right. Okay, so what I'm going to do now is try to apply that same idea to a new situation. Now, instead of getting a volume by rotating a graph, I'm going to just look at a higher dimensional graph. Right? We're going to look at a graph now of a function of two variables. This was not a thing in a single variable calculus class. Right? Anyway, so looking at that graph, here it is. If I want to compute the amount of volume that's under that graph, oh gosh, I may have bitten off more than I can chew on this. Okay, anyway, close enough. I want to compute that amount of volume. By the way, the amount of volume specifically sitting over a certain rectangle in the domain. Right? Obviously, the graph goes on forever. You can't compute all the volume. You have to specify over what specific rectangle. Okay, to this question, notice that I'm computing a volume just like I was here. Here I made sort of slices and added up the volumes of those little slices. How about I do the same thing here? I'll take little slices one at a time. And so here's a slice. Right? That little slice of volume. Now, what was the next move I did up here? Again, copycatting. The next move over here was to recognize that the cross-sectional area was a garden variety high school geometry formula, area of a disk, old news, no problem. And that's where I'm dead in the water here. Because this cross-sectional area is not garden variety, barnyard familiarity. This is not cows and ducks, right? This is a weird thing. That's not a rectangle. It's not a triangle. It's not a disc. So we stop there. Everybody see the problem? Okay, so now I'm going to make the observation, though this is one of the big observations, is that technically, in fact, I do know how to compute this area. Because don't think of this as an area of a slice of a solid. Think of this as it is the area under this curve. And area under a curve, that rings a bell, right? We know how to compute area under a curve. If you want to compute the area under a curve, you just need to understand what is this curve the graph of, and take an integral. So, looking at this purple curve, what is this the graph of? Well, here you go. Right? This is, every point on that curve is part of z equals f of x comma y. Now, we do have to think through what roles are being played by the variables here. We've got an x and a y. What's going on? What are they doing in this picture? And the picture tells all, by the way. I'm a big believer in when you're trying to understand this strategy that we're developing here. Make sure to rely heavily on this picture. It's extremely helpful. So notice in this picture, why are we here in the first place? We are here because we're trying to compute this cross-sectional area. And note that cross-sectional area is in a plane, and that plane is described by y being constant. So that means that y is constant there. I'm going to treat y like a constant because it is. The picture tells us so. Right? Is everybody on board? Again, my goal here, forget about the volume. We'll deal with the volume later. Right now I'm computing the area under that cross-section curve, and for the purposes of that calculation, every point in that area, y is a constant. Okay, so what is x doing, on the other hand? Well, this x right here is, in fact, still a variable, right? I need x to go from A to B in order for this point. Let's see here. Let me circle this in blue. For this point, x comma y, that I'm plugging into my function to actually go across the base here, like so. And then notice, having done that, y being fixed, x being a variable, x comma y then moving as the blue line does here, just right along the base, z, namely f of x comma y, is giving me these heights. And I know height times width is going to give me little pieces of area. And again, single variable calculus, I can add up all of those areas. So height is what I do an integral of as x goes from A to B, and that will compute my cross-sectional area for me. So again, area is this whole cross-section. This area that I'm trying to add up is computed with that integral. How are we doing? Is everybody with me? Okay. It's kind of all over at this point. We already agreed that the volume is going to be what I get when I add up the little volume slices. I know that the volume slices are area times thickness, just like in the rotated example. And I just kind of have to put the puzzle pieces together with these having already been established. And let me clear up my picture's a mess. Do like that. Okay, so we have computed this cross-sectional area. Area times, let's see here, thickness. These little thicknesses right? Little pieces of the y-axis. Thickness is dy. And I'm going to take those areas times, losing track of my colors, thicknesses, and I'm going to add those up as y now goes from C to D. Back over to this original picture. Keep in mind, that's what's going on in the y direction. For each value of y between C and D, we get a corresponding slice and therefore a corresponding piece of volume. So y goes from C to D, and thus y from C to D. What do you think? Everybody on board? It's morally not that different from this volume of rotation example. It's just that, well, yes, I'm going to compute volume with an integral, but the integrand, namely the cross-sectional area, is also an integral. So I literally have an integral of an integral. And so it's a little weird looking, a little creepy. An integral of an integral. Can you do that? Yeah, it's fine. You can totally do that. All right. Okay, yeah. Mm-hmm.
Yeah, given this idea, so the order of dx dy shouldn't matter, right?
Kind of. I'm going to come to that. That's a great question. And there is a version of this where the order is in the other direction. It does change just a little bit, not much. But you're on a good track. We'll talk about that in a few minutes. Yeah. Okay. All right. So terminology, by the way, integral inside of an integral. They call it an iterated integral. I think the motivation for the term iterated is that you're doing an integral and then you're doing another integral. My little personal complaint about that is, well, yeah, but you're doing two different kinds of integrals. So to me, this isn't really an iteration. To me, this is an iteration suggests you're doing the same thing twice. Very importantly, here we're not. So this has always kind of rubbed my fur backwards. It just kind of bugs. So I've been trying to popularize the term nested integrals, which I think really does make sense because we literally have an integral inside of which is another integral. Right? So I think nested works better. But anyway, whatever. I think I'm losing that fight, but we'll see. So iterated integral is the term. And I want to make sure we do keep track of a few things. First of all, you'll notice as I developed this integral, the dy integral was written first. Right? I established that volume was an integral dy, and then subsequently I started thinking about what is its integrand, the cross-sectional area, blah, 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 and only second did I, as a result of that, develop the dx integral. So the outside integral was developed first. But when you get around to evaluating this thing, and we're going to do one in just a moment, when you get around to evaluating this integral, you have to do the dx integral first. Namely, the inside integral is the one that's computed first. Because I can't do the dy integral yet. Until I've computed this dx integral, I don't even know what the integrand is for the dy integral. That make sense? You kind of have to develop outside in, but you compute inside out. So, as a result of that, the term, the first integral and the second integral, this is not clear. You mean the first one that was developed or the first one that we'll be evaluating in the computation? First and second is not clear. Easy resolution, just refer to inside integral and outside integral. Resolves that completely unambiguous. Good choice. Okay. Next point I want to make. Again, keep in mind the roles that the variables are playing at various stages. So while you are doing the inside integral, right, for the purposes of this inside integral, it's a dx integral, and of course x is the variable because it's a dx integral, so of course you treat x as a variable. After all, x is going from A to B. But the outside variable, Why? While you're doing that inside integral, while you're doing the dx integral, while you're computing this cross-sectional area, and again, make sure to remember from the picture what is actually happening. The whole purpose of that inside integral is to compute this cross-sectional area, and that's not even defined. It's not even a thing unless you agree that y is fixed for the purposes of that calculation. I need to know a value of y, for which you want to know the cross-sectional area in order to be able to compute that cross-sectional area. So unavoidably, the outside variable has to be constant. So this variable has to be constant while you're doing your inside integral. Everybody cool? So the upshot here is just you have to remember that as you're doing the calculation. Okay, let's dive in and do a calculation. Let's see here. Okay. So we're going to compute the volume under the graph of this function of two variables sitting over this rectangle in the xy plane. Real quick point of terminology or notation. This notation where you have a cross. This is not a cross product. This is a way of defining a rectangle, and the first interval is telling you the range of values of the first variable, in this case x, going from 0 to 1, and then the second interval here after the cross is telling you the range of values of the second variable, in this case y, and so altogether this whole thing is just a notation representing this rectangle in the xy plane. Everybody comfortable with that notation? It's just notation, but it's extremely handy, and we're going to be using it a lot, so heads up. Okay, so that said, we already have gone through an argument for how to compute a volume under a graph sitting over a rectangle. It's exactly what we already discussed, so I'm just going to go straight to, here it is. There's our integral. That integral gives volume under the graph. Now we just need to start computing. We've already discussed we have to start with the inside integral, and per this point above, don't forget, for the purposes of that inside integral, the outside variable is constant. So y I have to treat as a constant, and therefore y squared there is a constant. So many students will look at this and think, oh, y squared, I'm doing an integral. Isn't that like 1/3 y cubed or something? No, because it's not a variable. Y is no different from like a k, right? If you do an integral of k squared, it's constant, so you just get variable times k squared. That's it. And same deal here. When you integrate a constant, right, all you get is the variable times that same constant. Everybody good? Very common source of screw-ups. So heads up on that. Okay, the rest of it's pretty straightforward. Let's see here. The x anti-partial, the x antiderivative of x squared, just exactly as you would think, is 1/3 x cubed. Right? Old news. By the way, let me take this opportunity to remind y'all, Calc 2 it's in the prerequisite trail of this course. It is going to be expected and assumed that you are proficient with integration. So now I know this is an easy one, and I know you all remember the power rule for integrals. But please make sure also that you're really good with substitutions, integration by parts, basic standard trig integrals, and there's all these various little tricks that can be used to compute various different integrals. So just make sure that you're good with I'm going to say most of them. There were some obscure weirdo integrals in Calc 2 classes, hyperbolic cosecant. Don't worry about that. For the purposes of Math 219, we're not going to use hyperbolic cosecant at all. So ignore the obscure things, but the basic integrals, substitution, integration by parts, trig integrals. I'm a big believer in trig substitutions. I think you should know trig substitutions as well. Let me call your attention, by the way, while we're on it, to my miscellaneous topics playlist. I have a lecture here on trig substitutions. I encourage you to take a look. It's about, 30 minutes, right? You can fast forward as much as you like if you're bored and if you already understand certain parts of it. I encourage you to make sure that you're good to go on how to use trig substitutions. Okay. All right. So back to this. So we did that integral. And then let's see here. We have, when we plug in, x is going from 0 to 1. So let's plug in those values. Notice I have explicitly written, not just 0 and 1, but I have explicitly written x equals 0 and x equals 1. The reason for this is because this is the next opportunity for screw-ups. And I've seen this, again, a bunch of times. What happens is students are taking these numbers, they're plugging them in, and, there's a lot going on, and, let's plug in 1, and so you plug in the 1 for the variable, and then you plug in the 1 for the variable, and it's just all too easy to accidentally plug in the 1 into y because it looks like a variable. And it's just easy to forget. It happens to the best of us, right? So my little hack for avoiding that is to remind myself that only x do you plug in for, because after all, these are values of x. So I write down x equals instead of just the numbers. I encourage you to do that. You don't have to do it. I think it's a really good idea. It'll cost you a second and a half of writing time, and I think that's a second and a half well invested. Okay. Okie dokie. You plug these values in, and this turns into that, which you notice is a function of y, as it better be, because we're doing an integral dy. The x's are all gone. We've plugged in for them. So this is now literally single variable calculus. There is only one variable, single variable integral. Compute, answer. And we just computed the volume. Everybody happy? Cool. All right. Okay, now to your question. Yes, you can do this in the other order. I arbitrarily, no particular reason, started off by slicing in the y direction, and then subsequently finding myself to have to also slice in the x direction. So that's why we have y on the outside and x on the inside. So, what if you sliced it, instead of slicing like this? What if you sliced like that? Right? You still get slices, you still get little pieces of volume, etc. I am going to leave as an exercise for y'all. Again, I think this is a healthy learning opportunity to mimic, kind of copy even, but just, adapt it appropriately. Mimic the argument that I've done here to compute volume as this iterated integral, to come up with an equivalent if you were to slice the other direction. And two things are going to happen, just to let you know what the answer is. Obviously, if you slice in the order, the differentials are going to be in the other order. The other thing is, the bounds have to move also. Because after all, if x is on the outside, the range of values for x, the bounds for that x integral also needs to be on the outside, no longer on the inside. So this move right here. So you can do this with your bounds when you're integrating over a rectangle. You can just switch the differentials, switch the bounds accordingly, and it works just fine. And that's the statement that I make here. Notice that here, with the y integral from c to d is on the outside. Here it's on the inside. The x integral here on the inside, now on the outside. Gives you the same answer either way. Both compute the volume. Is everybody okay with this? Okay. Now, I do have to give you a warning. I don't want you to overinterpret my statement here. This business where you switch the bounds and the differentials together, this only works if your domain is a rectangle. We have only considered rectangles to this point. to be fair. But we will soon, as in probably on Friday, possibly today, I'm not betting on it, but anyway, sometime very soon we will be talking about domains that are not rectangles, and how do we deal with that. And very importantly, this goes out the window. You cannot, it does not work, it just doesn't work. You cannot do this switch in the bound, switch the differentials, and it all stays the same. Not true. Okay, so let's see here. Now, here's an awkward point. Let's think about single variable integrals for a moment. What do we compute with single variable integrals? And a lot of students like to lean on what I consider to be the crutch of thinking of single variable integrals as computing areas under graphs. I'm going to give a little bit of a speech about this in a second, and that is that that is a point of view. It is nice, I guess, but it's rarely actually what we're interested in computing. It's usually just like I say, a geometric intuition. It's also not really a very good point of view on how to compute things. I am getting a little ahead of myself. But the area under a graph is that's just one of many things that we compute when we're doing single variable integrals. So likewise, computing volume under a graph that we just did, this is only one of many, many things that we're going to be computing with as we do integrals. Anyway, I haven't defined the term yet, but this kind of thing, let me just say, is we're going to be computing many more things other than just volume. So now with single variable integrals, among other things, we computed mass, like mass of a one-dimensional rod or something like that. I'm sure y'all remember those applications. So let's ask, can't I just do this same thing? Can't I just do an integral of an integral? And instead of multiplying height times length times width and thus getting volume, can't I just think of mass per unit area times length times width, which is kind of an area? Shouldn't that give me mass? Why can't I just write this down? And the thing is, you can't. It doesn't make any sense. And let me try to emphasize why. When we're doing this integral up here, I remind you that for the purpose of this integral, as you're computing that inside integral, which you have to do first, I can't even talk about the y integral yet. I don't even know its integrand. Right? For the purposes of computing this inside integral, y has to be constant. So while I'm doing this, I can't talk about dy. There is no dy. Y is constant. So what I have to focus on first is how to make sense out of this. Right? F times dx. And can I make sense out of that? Yeah, no problem. That's height times length. Sure. Height times length is a pre-existing concept. That's called area. Not only is it a concept that I can give a name to, it's something that I understand. Area does what I call accumulation. I can compute the total area by adding up a bunch of slices of area. Right? And I can say that that's true because I see the picture of area in my mind. I understand what area looks like, and it's just straight up clear that the area of slices adds up to the area of the whole. Okay, well, now let's try to do that same thing down here. Again, just kind of copycatting. Fingers crossed, hoping this works out. If I'm computing mass and I have density in here and I try to make sense out of this thing, right? Well, I've got my integrand is mass per unit area. And what am I multiplying it by? I'm multiplying it by, again, length. And that's just not a thing. Mass per unit area is intended to be multiplied by area. If this said mass per unit area times area, then I'd be able to say, yeah, that's mass. I understand mass. And mass is a intuitively clear thing. I understand how it behaves. I have intuition for it. But this, mass per unit area times length, I guess I could, wouldn't that be mass per unit width, maybe? right? You could try to make some sense out of that, and sense can be made of it. But the problem is, it's something I would have to make sense out of. It's not a pre-existing, intuitively reasonable concept that we already understand. In this application, mass is not distributed across widths. It's distributed across areas. Right? So, I mean, think about population, distributed across area, right? That's where people live. We live on area, surface of the earth. And I talked about population per unit area. What would population per unit width mean? This is weird. I don't know what that is. Right? And even if I could make sense out of it, and even if I could establish that it behaves the way I need it to, that it accumulates, that I can think of it as accumulating as I, add up over all the pieces, I would have to go through this same conceptual discovery for every single application I can ever come up with. I'd have to do it, when I'm computing population. I'd have to make sense out of population per unit width. It'd be a whole new thing. And if I were computing the amount of work that it takes to accomplish a certain task, brand new concept I'd have to make sense out of. This is not feasible. Right? So I want to emphasize, this is, so again, I trash talk partial derivatives right after we define partial derivatives as being very limited. Is really not the way to think about things. And so I'm doing the same thing here with integrals. Iterated integrals are really limited. They only directly compute the answer to one question. Because it just happens to be that one question, there's, the mid-process concept happens to be a pre-existing geometric concept. We got lucky. Everybody see what I'm talking about? So, I don't want to say I don't like iterated integrals, but we need to understand how limited they are and what they're good for. Okay. All right. Okay, so how are we going to answer mass questions then? How are we going to chop things up into little pieces and add them up? Before I get to that, I want to remind you about single variable integrals. A lot of people misunderstand. Again, I'm going to try to restrain myself on how much time this is one of my standard soapbox speeches that I also have on my miscellaneous topics playlist. What is an integral? This is a fantastic, it's a great representation of my opinions, take that for what it's worth, about single variable integrals and how they're very often misunderstood. High school calculus classes very often commit pretty serious math crimes and misrepresent things. And anyway, if you're curious, if you feel like you might be able to benefit from a better understanding of why, for example, Riemann sums are important, that's a good video to watch. So anyway, for your consideration. Reminder though, an integral is defined as a Riemann sum. This is the definition of an integral for our purposes in this course. Again, I've already said some of this, and I'm going to try to keep myself contained on this, but please do not think of an integral as a construction whose primary goal or task is to compute areas. It's really not. It's I'm going to say anyway, rare that what we actually want to compute is area under a graph. Sometimes, comes up, I suppose, if I have a room in my house and I want to paint one of the walls and the top of the ceiling has a variable height or something, and I need to know how much area literally is on that wall so I can buy the right amount of paint. Yeah, I guess that's area under a curve. Notice what a weird circumstance that is. Most of the time, when you are computing stuff with integrals, most of the time it's not area. Most of the time it's other things here. It's mass or work or probability if you're doing calculus-based statistics, or population, whatever. There's a bunch of stuff. Okay. So mostly not what integrals are for. And also, very importantly, very rarely can I use area as an actual tool in a computation. This is again, one of the big math crimes that I think high schools commit. They'll take a question like, we want to compute the amount of work needed to perform a certain task. Right? Y'all have seen a million of those applications, and if you try to say, of course work is area, I have to pause and say, I'm sorry, what? Work is what now? Why is work area? This is not clear. This is a problem, right? So very importantly, we make the definition of integral Riemann sum. It's this expression here. Because if you have a question like, I want to compute the amount of work that it takes to blah, 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 well, I can take that work, I can chop it up into various little pieces, and I can represent that calculation as a summation that looks something like this, namely a Riemann sum. So I can immediately connect applications to Riemann sums, not to area. And in fact, by the way, if you did want some high school calculus classes try to avoid this. I still don't really understand why, but they try to avoid this harsh reality that we need Riemann sums by doing some sort of mental gymnastics where they try to connect work to area, but they end up doing it by way of slicing things up into little pieces and adding them up daily by doing a soft use of Riemann sums, right? But fundamentally, one way or the other, you need Riemann sums. All right. Okay, so that's enough on this point. So strategically, when you do a single variable integral, you take your application, you write it as a Riemann sum, aka an integral, and then we have the fundamental theorem of calculus to plug and chug. Okay, so we're going to try to do something kind of analogous. Let me come back up here real quick. What is a Riemann sum? Why is it that Riemann sums are so useful in computations? Well, because we have some question that's hard, but we find that if we take the domain and chop it up into little pieces, on each little piece, the question is easy. If you're computing area under a curve, well, on each little piece, it's a rectangle. It's height times width. If you're computing work, well, over the entire length, it's a complicated question. But on each little piece, no problem. Force times distance. Whatever. Right? So we chop it up into little pieces where the question is easy. And then we add up over all of those pieces. So I like to summarize. I like little pithy little memory tools, and my little pithy summary for what is a Riemann sum and why do we do it. The action of this process is I summarize by chop it up, add it up. You're going to take your domain, your hard problem, you chop it up into pieces over which the question is easy, and then you add up over all those pieces. Excuse me. So we're going to try to find a way to do a chop it up, add it up strategy now on rectangles instead of intervals. Pause. Questions? Cough. Oh, gosh. Everybody all right? Okay. All right, so adding up over a rectangle. Well, here's my rectangle, and what would it mean to chop up a rectangle? Well, I kind of have to chop two different directions, don't I? I have to... I missed. Oh, well. So I have to chop up that way. That doesn't give me little bitty pieces. This gives me long, skinny pieces. So I have to chop up the other way as well. Close enough. And having chopped up in both directions, then that leaves my large rectangle left as a bunch of small little pieces. And the hope and the idea, and by the way, what we're going to find to be the reality of it, is that, yes, we can turn a huge number of questions, a huge number of physics problems, engineering problems, economics problems, biology problems, whatever. We can take hard questions that happen over an area, we can turn them into easy questions that happen over little bitty sub-rectangles, and then we just have to add up over all those little sub-rectangles. That's it. details we have to worry about. But basically, chop it up, add it up. It's just now we're chopping it up into little pieces of area. Okay, now, yes, there's a bunch of details. We have to say this stuff because we have to note for the record exactly what do we mean when we write down our stuff. But here's the idea. As we go from A to B and we chop that up into a bunch of pieces, that's old news. I already know what delta X is. I already know what XI is. Y'all will recognize those formulas in green from Calc 1, Calc 2, wherever they do that these days. That's hopefully you've seen all those formulas. So, here's the thing. I'm also going to be slicing up the interval on the y-axis from C to D, and that just gives me analogous formulas. Totally analogous. They're not the same. I mean, it's different. It's C to D instead of A to B, but morally it's the same ideas. Little details that I do have to keep track of. Knowing where you are, which one of these points are you looking at? Where in the slicing process are you? We use I as a subscript and a participant in the equation to keep track of which one of these slices I'm in on the x-axis. Well, now I has a purpose. I can't use it for another purpose. I can't confuse my indices. So I have to use now, instead of I, when I'm keeping track of where I am on the y-axis, I use J instead of I. I mean, it's, again, serving the same purpose, serving an analogous purpose, but, different letter. Whatever. And all of this documented. I can now write down my chop it up, add it up strategy. If I look on a little piece here, little piece of area, the whole point of breaking it up into little pieces is that whatever my question is, and I emphasize, what application we're doing here, I don't know. I want to keep this flexible. I want this strategy to be applicable to lots of scenarios. So I'm not going to say yet what F is. But you could imagine, and we're going to see many examples, that there'd be lots of situations where on a little piece of area, some function times area is going to be the answer to the question on that little piece of area. So this is analogous to the single variable story. And so integrand times area. Of course, area is delta x times delta y. Everybody good? So that's the chopped up question. And then I just need to add up over the entire rectangle. Well, don't forget that over that entire rectangle, I need to look at not just all n of them. There's actually n squared of them. Not only does I go from 1 to n, moving me horizontally, j goes from 1 to n, moving me vertically. I've got to go in both directions. So this summation, you'll notice, has both j and I going from 1 to n. So there's, again, n squared terms in that summation. Is everybody with me? Take a limit to make round-off errors go away. Boom. That's a strategy. This is the rip-off of the single variable Riemann sum strategy into a multivariable setting. So I'm going to call this a 2-index Riemann sum because there's two different directions. There's everything's two-dimensional. This is going to be super useful. We're going to compute lots of stuff with this strategy. It's so useful that the expression representing this strategy deserves a name and a notation, and here it is. Maybe I'll keep it here just for the moment. So we can see what we've got here. This expression is called a double integral. We have a notation for it. I think the notation's pretty believable. There's the notation. Notice very conveniently this delta x, delta y. Why did we write down delta x, delta y? It's because it represented a little piece of area. So I'm going to use dA. This is extremely standard, right? I didn't make it up. And then we've got this summation that's happening. let's see here, the summation, but we're adding up in two directions. I goes from 1 to n, but also j goes from 1 to n. We're adding up in two different directions, and so I'm going to use, and again, very standard, I didn't make this up, we're going to use two integral symbols. And there you go. There's our notation. Now, of course, I've got to tell you what the domain is. We have to be clear what the domain is. The domain is going to be a rectangle like this. And so we usually just make that a subscript. It's kind of an easy, convenient way to do it. And there you go. That is double integral notation. How we doing? Yes?
It's a rectangle. Why did both I and j go to n?
No, because I arbitrarily chose that I was going to take this and chop it up into n pieces. And so my goal here is not to chop up pieces into a certain size, right? As I have it drawn here, this is longer than that, right? And so there's tempting to say, well, if I wanted them to be the same size, then yeah, there'd be more of one and less of the other. But I'm just not, right? However big this is, I'm going to chop it up into n pieces, and however big this is, likewise, I'm going to chop it up into n pieces. Yes, these pieces will not be squares. No problem. Is that cool? Yeah. Okay. Now, I want to call your attention to something. Here's an underappreciated point. A lot of people don't seem to get why we would care about this. But this double integral, is not the same as an iterated integral. Here, I'm chopping up a question into n squared little pieces, and I'm multiplying integrand times area. That is very, very importantly not what we're doing here with iterated integrals. With iterated integrals, you're slicing into n slices. You are multiplying first your integrand times not an area, times a width, a length, whatever. While you're doing it, the other variable is constant. Right? So it's a very different strategy, very different construction. These are not the same expressions. Yeah. Everybody with me? All right. Let's make an application of this. You want to compute the volume under a graph? Well, we've done this already. We already know an answer. We know that iterated integrals will crush this question. But notice also, I can view this little piece of volume here over an area. Forget about slices. We're not taking little slices. I'm making French fries out of this thing, right? And that little French fry has a volume, and that volume is height times the area of the base. I mean, boom, right? It's very easy question on that little sub-rectangle. Is that cool? Yeah. And then, of course, notice that having done so, I find myself with an expression which is exactly a double integral. So double integrals compute volume just fine. Okay. All right, and but let's not lose sight of the fact that I've already computed volume with iterated integrals. So now that I have computed volume with double integrals, I'm computing the same thing with two different strategies, and that means that these two different things are also equal. So if you have a double integral, you can compute it with an iterated integral. Okay. All right. Okay. So we've done a lot of stuff here. We've developed a lot of ideas. I like to have a diagram representing what arguments have we made here. It's hard to keep track of this. Here's the first thing we did. We had the very narrow, focused question of computing volume under a graph. We created iterated integrals. You can crank it out with the fundamental theorem. Just keep track of what's a constant, what's a variable, details. But that was the first thing we did. Okay. But I pointed out that you cannot use this to compute the answers to other things like mass. You just can't write down a mass question directly as an iterated interval. The units just don't make sense. The concepts don't fit together. It just doesn't work. So you cannot use that like so. And I've also pointed out that you also cannot take geometric or physical or whatever things like work or mass or probability, whatever. You cannot just declare them to be volumes. They're not. They're really different things, and it's not clear why they should be considered volumes. So you can't do that either. So here's why double integrals are so important. Double integrals, when we add double integrals to the equation, when we make this connection that double integrals also compute volumes, just like iterated integrals compute volumes, and therefore that I can compute double integrals with iterated integrals. This is what we did just above, right? Double integrals then allow us to supplement our diagram in such a way that I have a strategy for computation. You can get there from here now. And if you want to find an answer to an application, step 1, write it as a double integral. I want to hear about volume. Volume doesn't make sense, right? You cannot just write down an iterated integral instantly. That doesn't make sense either. But you can write it as a double integral. You can then subsequently declare that your double integral is computed with an iterated integral. We've established that. That is a nice little point. Thank you, volume. Volume was the thing that allowed us to make that connection, but we don't really need it anymore. And then thirdly, the iterated integral, just like before, you crank with the fundamental theorem. So this is our 3-step process. When you're going to use a double integral for calculations, I need to see all 3 of these steps. That's the argument. Good place to draw the line. See y'all on Friday. Have a good day. Yeah.